Okay, so here's where we left off last time. We hadn't quite gotten to this, but here's the next thing that we're talking about. So remember, we're talking about eigenvectors and eigenvalues, and we talked about how to find eigenvectors and eigenvalues. A couple of methods, processes for how to do that. But then also recall, we set up a kind of an analogy. We started to notice that the process of finding eigenvectors had a lot in common with the process of finding homogeneous solutions to differential equations. Right? So there's a characteristic polynomial in both cases, whose roots ultimately are what give you these solutions. Quite different algorithms, of course, but nevertheless, polynomial roots leads to solutions. And that's kind of an interesting pattern. The pattern is not perfect, of course, and we did see last time that how many eigenvectors you find is not always equal to the multiplicity. The number of homogeneous solutions that you find in Chapter 4 is always equal to the multiplicity. That always works perfectly. Spot on match every time, no exceptions. Not with eigenvectors. Okay, so here's the consolation prize, though. While the number of eigenvectors you find is not always equal to the multiplicity, there is a relationship. The number of eigenvectors that you find is always less than or equal to the multiplicity. So, like I say, consolation prize. It's not the same, but it's not nothing. Right? There is a piece of information there. Okay, the number of eigenvectors is always less than or equal to the multiplicity. Now here's, let me not get ahead of myself. This is a hard thing to prove. We're ultimately, in fact, not going to prove that in this course. We are going to relate this to another fact later on, but we're not going to prove that one either. So ultimately, we're not going to prove this. But here's something you can prove, and I think everyone should do this on their own. It's a lovely little exercise, and that is prove that the number of eigenvectors you find will always be at least one. If you have an eigenvalue, in other words, a root of your characteristic polynomial, there will always be an eigenvector. It's not a hard proof. Roughly speaking, the proof goes like this. If you have an eigenvalue, you have a root of the characteristic polynomial, that means that a certain determinant is 0. That means that a minus lambda I is singular. And if a minus lambda I is singular, I refer you back to that long list of equivalent conditions at the end of Chapter 2 that we wrote down on the board here. Matrix is singular means that the null space is at least one-dimensional. Okay, and don't forget that null space is where you find the eigenvectors. Okay, so that's the outline of the proof. I think it'd be a nice exercise. Write that down. How do you take this assumption that you have an eigenvalue? How do you show that there is at least one corresponding eigenvector? Good practice proof. Okay, so what can we get out of this fact? The number of eigenvectors that we find will always be at most the multiplicity. There's a nice consequence of this, and that is this little story right here. Best case then, right? The most eigenvectors you could possibly find. For each eigenvalue, the best case is the multiplicity. Right? That's what this says right here. Well, if in each case the best case is the multiplicity, that means that grand total, the total number of eigenvectors that you could possibly find, best case, is the sum of all the multiplicities of all of the roots. In other words, it's equal to the degree of the characteristic polynomial. In other words, it's equal to the number of columns in the matrix. So, nice conclusion. At most, your total number of eigenvectors is n. Okay. Yeah.
What guarantees that eigenvectors will be independent?
Oh, so this is what we were talking about. This is a sort of a consequence of language. I mean, if you really ask how many eigenvectors do you actually find, it's infinity, right? You always find infinitely many. So when we say how many eigenvectors, that's really sort of slang for how many eigenvectors in a basis for that vector space of eigenvectors. Right? And a basis is by definition independent. So this, when I say the most number of eigenvectors, when I say linearly independent eigenvectors, I mean what's the maximum number of vectors in a basis for that null space? Yeah, right. Okay, so let's take a geometric point of view on eigenvectors real quick. Y'all will recognize that matrix. We've computed the eigenvalues. We computed the eigenvectors. We did all this last time. Make sure you remember what those processes are. But geometrically, what does this tell us? Let's think about this pair here. We have an eigenvalue and an eigenvector. There's the eigenvector right there. Let's say 1, -1. Well, don't forget, when we say we have an eigenvector, we're actually talking about all of the vectors in the span of that eigenvector, right? Because any multiple of an eigenvector is still an eigenvector, right? When you solve for the collection of eigenvectors, you're always going to get a null space. You're always going to get a vector space. Okay. So what we're saying is that the matrix does something nice to this line. Now, what does the matrix do to this line? Well, the action of multiplication by this matrix on this line, any vector that's a multiple of this, effectively we're just multiplying by the eigenvalue. We're just multiplying in this case by 4. So this vector here, the action of the matrix on that vector is to multiply it by 4. And same story for all of the other vectors on this line. The matrix simply takes that line and everything gets stretched out by a factor of 4. So there's a really nice kind of geometric interpretation then of this being an eigenvector. The matrix preserves that line. Everything on that line goes to something else that's also on that line. And it preserves that line by stretching by a factor of 4. That's kind of a nice interpretation. Likewise, let's look at this eigenvalue eigenvector. The eigenvector 3, 2, something like that. Okay, well, actually, all multiples of that are also eigenvectors. So every vector on this line, the action of the matrix is to simply multiply by the eigenvalue. That means that every vector, for example, this one on that line, has an image that is, well, just -1 times the original vector. In other words, the action of this matrix is to preserve this line. Everything on this line stays on this line. And specifically, what the matrix does to this line is kind of flip it over by multiplying by -1. So anyway, so this is a nice point of view. You can think of eigenvectors and eigenvalues as giving you a nice geometric interpretation of the linear transformation that this matrix represents in terms of what it preserves and how things get stretched on those sets. Okay. Analogously, I'm not going to go through all the details of this example, but I just want to show you what happens when you have multiple eigenvectors for a given eigenvalue. So remember this example, we studied this matrix, found the eigenvalues, there they are, found the eigenvectors, there they are, flashback to last time. Right? These eigenvectors, that and that. Okay, well, I don't mean just those eigenvectors, of course. The way you find eigenvectors is you're actually finding a null space of A minus lambda I, so you're actually getting a vector space. What we call the 2 eigenvectors that we found, this is really just a basis for the complete collection of eigenvectors. We actually have infinitely many eigenvectors. This whole plane, the span of that basis that we've written down, that's really the eigenvalue. All of those vectors are eigenvectors. And what does the linear transformation do on that plane? Well, every vector, in that plane, when you multiply by the matrix, you're effectively multiplying by the eigenvalue. Everything on this plane gets multiplied by -1. Said differently then, this plane is preserved. Every vector on this plane has as its image another vector on this plane, and the action is everything gets multiplied by -1. Or you might say everything on this plane gets sort of rotated around. This plane gets rotated around 180 degrees. You might say. Okay. Alrighty. Last thing I'm going to say about eigenvectors, in section 5.4 anyway, is to observe that sometimes you get complex eigenvalues and sometimes you get complex eigenvectors. It's a little uncomfortable because if you're starting with a real matrix, there's a temptation to say it started off real. This question is about real stuff. If you have a real question, shouldn't you get real answers? It feels like it should, right? But let me remind you, we saw real differential equations that had complex solutions. It just happens, right? Likewise here. Real matrix, but it can have complex eigenvalues and complex eigenvectors. Ultimately, no surprise, because everything comes from the characteristic polynomial. Polynomials have a sad feature that even if they have all real coefficients, they might have complex roots. Old news, right? So no surprise. All right, so let's see one in action. Here's a matrix, all real coefficients. By the way, this represents a rotation, whatever that's worth, pi over 2 counterclockwise. So this matrix, write down the characteristic polynomial. There it is. It happens to be lambda squared plus 1. When you, therefore, look for the roots of the characteristic polynomial, keep in mind roots are eigenvalues. Well, here they are. They are complex. Can't help it. Let's find the corresponding eigenvectors. Well, again, one at a time. That eigenvalue, plug that into a minus lambda I. For that eigenvalue, this is the null space I need to compute. How do you find this null space when the matrix is complex? Same game. It's really not at all different in terms of a process. Row reductions, when there's complex numbers involved, it's just a row reduction. And so now, admittedly, give me 2 seconds. Admittedly, the arithmetic is a little annoying, right? So for example, the very first thing you might want to do, I suppose, is to maybe let's divide by -I to kind of clean up that. You want a 1 in the top left, right? So maybe you want to divide by -I. How do you divide by a complex number? Well, y'all remember how it's an annoying little process, but it's arithmetically inconvenient, but as a process, it's the same thing. Here's the reduced echelon form. Solve for your pivot variables in terms of your free variables. There's your eigenvector. Yeah, question.
Is there a strategy for solving this when you create this matrix and get 1 minus I or some sort of expression rather than just individual value?
The answer is the same as it was for real matrices that you want to row reduce, and that typically I like to think of fixing one column at a time. Start with the left, move to the right. But there are little clever moves you can pull every now and then. For example, in this case, maybe you switch the first rows, the first and second rows to start off with. So clever moves here or there, but ultimately it's just a row reduction, and so one column at a time, left to right. And with some exceptions, if you get lucky breaks or if you have some clever insight. Anybody else while we're on the topic? Everybody's good? Okay. So eigenvalue, eigenvector. I think it's a healthy exercise. Everybody should do this. It'll only take you a few seconds. But let's directly confirm, you guys, I would like you to directly confirm that in fact this is an eigenvector of that matrix and that the eigenvalue is I. The way you're going to confirm this, keep in mind, the definition of an eigenvector and an eigenvalue is that A times eigenvector gives you eigenvalue times eigenvector. So just compute matrix times the eigenvector. Compute eigenvalue times the eigenvector. Observe you get the same thing. direct confirmation that it works. Okay, so for this eigenvalue, we played the game. We got the eigenvector. We then, of course, have the other eigenvalue. Now that other eigenvalue, same game. Eigenvalue, a minus lambda I, row reduce. Solve your pivot variables in terms of your free variables, and eigenvector. Okay. Neat fact, though. Surely you already noticed that these two eigenvalues were conjugates of each other. And you may recall that this is a true fact when you have a characteristic polynomial with real coefficients. Any polynomial with real coefficients, complex roots come in conjugate pairs. So this is really old news. Here's the neat fact that is not old news, not hard to prove, but nevertheless not old news. Not only are the eigenvalues predictably conjugate pairs, so were the eigenvectors. This, and that are conjugates of each other. So the eigenvalues pair up as conjugates, the eigenvectors pair up as conjugates. Neat fact. So, in other words, after you've done that blue calculation up there, you found your first eigenvalue, you went through, found your first eigenvector. Technically, you don't even have to do the second calculation. For the conjugate eigenvalue, you know that you just take the conjugate eigenvector. And that's what this theorem says down here. This theorem is proved in the book. I would encourage you to take a whack at it yourself. This is not a hard thing to prove, that when you have a eigenvalue and eigenvectors, the conjugate is an eigenvalue with conjugate eigenvectors. That's really just a couple of details to directly confirm. Okay. Alrighty. Moving on. Section 5.5 is another big one. Let me just remind you, I'm sure you recall, Section 4.2 was huge. It took us like 3 days to get through Section 4.2. Section 4.5 was huge. That took like at least 2 days. I forget. Section 5.3 with change of basis was big, right? It took a while to make our way all the way through 5.3. 5.5 is just another big one. There are some really big ideas here in Section 5.5. It's really exciting ideas. It's more exciting for me than it is for you because I know where this is going. But let me just, again, all I can do is foreshadow, right? Because there's a lot of turf we have to cover. There's a lot of things I need to define, facts that I need to establish, concepts I need to familiarize before you can see the big applications we're going to get to. But what we're going to do here in Section 5.3 is kind of where things come together in a way that's going to give us the tools that we need to solve a otherwise very scary collection of differential equations. We're going to be facing a very hard problem in Chapter 6 of a certain category of what we call systems of differential equations. And the big baseball bat that we're going to break it open with is this thing called diagonalization that we're about to talk about today. So anyway, exactly how that works, again, we can't talk about that right now, but this is going to be a big deal for us. Okay. So, diving right in, starting with a definition, I'm going to define this word called similar, what it means for two matrices to be similar. Two matrices, A and B. We say that they are similar if we can come up with some matrix P, some invertible matrix P that allows B to be computed as P inverse A P, which is a weird little formula, right? But that's the definition we're going to work with. There is something nice about this definition, and that it's very succinct, right? It's very precise. It's exactly what we mean by, what is this formula? Well, there it is. Okay. Let me tell you what I don't like about this definition. It is completely opaque. in terms of why would we ever care, right? Who cares if some matrix can be computed from another matrix by way of this wacky little formula? It's really not clear. Right? Here's another thing I don't like about this definition. Why are we using the word similar here? Right? That's a loaded word. You say that two things are similar, the subtext, the clear implication is you're saying that those two things have something in common. How does this suggest that A and B have anything in common? Right? Not clear. So there's some bad things about this definition, and that's annoying. Now I do have to talk a little bit about language. There are certain terms that we're going to be using. So just for your terminological future reference, this construction, the action of taking something and multiplying by an invertible thing on the right, followed by its inverse on the left. This construction that you do, in this case we're doing it to the matrix A, that construction is called a conjugation. In this case we would say we're conjugating the matrix A by the matrix P. Or I suppose you might say we're doing the P conjugation of A, if you like. But anyway, the word is conjugation. A variation of that is that the result is called a conjugate of the original matrix. So we can say A and B here are conjugates of each other. It's just a little terminology, just FYI. And by the way, just a cultural point, there are other contexts where this construction, even when you're not talking about matrices, but the idea of multiplying on one side by one thing and on the other side by the inverse, there are many other types of situations where you're dealing with different types of objects where that construction is really useful in ways that we have not yet seen. So this terminology is very common for that, largely for that reason. So heads up, conjugate means that little construction right there. Now it remains that it's still not clear why we are using this loaded word. Okay, so that's the first thing I want to talk about in this term. What is it that A and B have in common that would justify this choice of term? Okay. Flashback to last time. Here's how you do a change of basis for linear transformations. Right? Just a quick reminder, if you're understanding T with respect to and by the way, this is the special case where you're viewing same basis for the input and output in both cases. So if you understand T with respect to one basis, and you would like to understand T with respect to a different basis, then, remember we drew that great big prism-shaped three-dimensional diagram and thought about the different matrices that play different roles in that picture, and we justified this formula. Right? Okay. Why are we digging up the past? The reason why is to notice that what we have here, just like there was a conjugation here, notice that there is a conjugation here. At least in this special case where these two bases are the same and these two bases are the same. It just turns out that change of basis on a linear transformation is a conjugation. Okay, so now you see the connection, right? So that conjugation structurally looks just like this conjugation. Okay. Now, then you might say, okay, well, yeah, but above that says any invertible matrix. Down here, this does not appear to be just any invertible matrix. This is a special matrix. This is a change of basis matrix. How do we know that every invertible matrix is in fact a change of basis matrix? I'm just going to assert for the moment. I'll come back and prove this later, but I'm just simply going to assert for the moment. Please take my word for it temporarily. Every invertible matrix is a change of basis matrix. It really is. And we'll see that momentarily. It's a detail that's not hard to prove. Okay. So here's the upshot then. This formula that we use to define similarity we have an alternative point of view on it. That formula for similarity could be reconceived of as this. So this assertion that A and B are similar is the same as the assertion that these two matrices are similar. And from this point of view, we have a pretty clear answer to the question that we were complaining about a minute ago. We were complaining about the use of this loaded word, similar. Similar suggests that the two things have something in common. What in the world do those matrices A and B have in common? Not clear. But what do these matrices have in common? No problem. These matrices have in common that they represent the same underlying linear transformation. Right? So that's why we use this term similar. Similar suggests something in common between A and B. They do have something in common. Two similar matrices represent the same linear transformation. Just, in different languages. That's a very important thing for two matrices to share. Right? Matrices represent linear transformations. It's one of the primary purposes of matrices. So two matrices representing fundamentally the same underlying linear transformations, very big deal. How are we doing? Everybody on board? Is that a question? Yeah.
That would be a better definition.
Better is a subjective word. Very often mathematicians like to choose as definitions that which is as crisp and succinct as possible, which is not always the same as the one that is most intuitively communicative, right? And I think this is a pretty good example of the distinction, right? So what I use as a definition here is, it might not be very satisfying, it's not very intuitive, but it is short. So there is something desirable about that. This other point of view, I think, is more certainly in the example that in the case of what we're thinking about here with matrices. This is more meaningful. This communicates more, as I've been kind of saying. And they are equivalent definitions. We could have made this our definition, sure. I'm sticking with the book's choice. Certainly when you think about the word similar, two matrices being similar, I strongly encourage you to think this. Also think that, but really think this. Okay, great question. Thank you for that. Anybody else? Okay. By the way, while we're talking about similarity, why do we use this term similar? Loaded word suggests two things have something in common. What do they have in common? Well, we figured that out. Let me just point out, this is not our first time down that little road. There is a past circumstance where we have used a word that was a loaded word that suggested that two things have something in common, and where we can identify what is that thing that they have in common. This goes way back to chapter 1, section 1.1. The word was equivalent. Right? So let's just walk through it. What does it mean for two matrices to be equivalent? I think different ways you can think about it, right? So two matrices are equivalent if you can get from one to the other by way of row operations. Well, I would call that equivalent. What is that? What do they fundamentally have in common, though? Two matrices are equivalent if they have the same underlying homogeneous solutions, right? That's what we were fundamentally talking about when we were in chapter 1. We were talking about solutions to systems of equations. Let's focus on homogeneous solutions. We're interested in solutions. That's why we were talking about matrices in 1.1. We're looking at solutions. A matrix was, might say, simply a way of representing, perhaps inconveniently, representing a set of solutions. That's what we cared about. So taking a matrix, for which the solutions is what we cared about, row reducing, this process of doing, turning this matrix into that other matrix, the reason, what those matrices all have in common, the whole point of that process was that they didn't change the solutions. So here we are again, same sort of semantical structure, equivalent. Two matrices are equivalent. Suggests that they have something in common. They do have something in common. Equivalent matrices have the same underlying homogeneous solution, the same null space. Anyway, I think that analogy is useful. And I have to really try to not inadvertently then make the really terrible pun or wordplay or whatever to say that the notion of similarity and the notion of equivalence are kind of similar, right? I really do try to avoid that. I say that just so you'll know what I'm trying not to say, right? But I might inadvertently do that. Okay. All right. Now I owe you a demonstrate. I claimed that every invertible matrix P is a change of basis matrix. That was sort of integral to how we made the connection between the top point of view and the bottom point of view. Now I owe you a proof. Why is it that every invertible matrix is a change of basis matrix? Here it is, theorem and proof. If you give me an invertible matrix, it is a change of basis matrix. I'm going to leave the details for you guys to check through on your own. Please, I think this is a nice exercise, so I hope you'll do it. Here's how you do it. That invertible matrix, it has columns. Those columns, I claim, are a basis. Chapter 2 fact. That basis is V. You can compute this change of basis matrix, and if you compute that change of basis matrix, you will find that indeed you do get P. So whatever invertible matrix you give me, that's how you can view it as a change of basis matrix. Details for y'all. Think through. I left some gaps in there. Think through those details. As always, when I give you these suggested exercises, feel free to ask me in office hours. Feel free to ask your TAs in discussion section or their office hours or whatever. Okay. So this sets up a way for us to talk about this next idea. This is going to be this is what's going to allow us to solve some differential equations later on. So many details we've got to cover first. Forgive me. We're going to talk about what it means for a matrix to be diagonalizable. It's a big word. What does it mean for a matrix to be diagonalizable? Matrix is diagonalizable if it is similar. There's that word again. We just talked about it at length. Similar to a diagonal matrix. Now, what does that mean? How do you think about this diagonalizability? Right? So here's how I think about it. The obvious, the brute force, the blunt first way you might think about it is diagonalizable means, what is similar? Similar means conjugate to a diagonal matrix. In other words, your diagonalizable matrix, that there's some way to conjugate it and have the result be diagonal. Why would I care about that? Who cares about conjugation? What's the point to that? Not very satisfying, is it? Here's then my preferred way to think about similarity. A matrix is diagonalizable if it's similar to a diagonal matrix. Here's a diagonal matrix, but let's just now, phooey on conjugations, let's think about our preferred way to think about similarity. Similarity means that by way of a change of basis, these two matrices represent the same linear transformation. Right, so let me say that a little bit differently. A matrix is diagonalizable if, but keep in mind, when we say matrix is really just a tool to represent a linear transformation. When we talk about a matrix being diagonalizable, what I'm really talking about is this linear transformation that the matrix represents. And what we're saying when we say diagonalizable is that linear transformation, you're just looking at it the wrong way. You're thinking about that linear transformation with respect to a bad choice of basis. And that if you were to simply look at that linear transformation with respect to a clever choice of basis, that you would get this really nice diagonal matrix. In other words, let me say that a little bit differently. A matrix that is diagonalizable represents a linear transformation that is fundamentally simple in the sense that a diagonal matrix is simple. So you see, that's pretty kind of interesting concept, right? That a matrix represents a nice linear transformation, and that, you know, maybe it doesn't look nice because, well, you're looking at it the wrong way, but that there's something fundamentally nice about that linear transformation. Everybody see this point of view? So alternate point of view on what that word means. Two different ways to think about it. I think this is much more satisfying, right? That the word diagonalizable means a linear transformation is simple. That's relatable, right? But this whole business about conjugation is a little bit hard to relate to. Yeah.
For the two matrices that are the matrix which is reference to the linear transformation.
Yeah.
Both of them have
the same domain for the ins and outs.
Yes. Is that necessary?
Yeah. We're going to stick with that. That's we have to have that because in order for this to actually be a conjugate, then those have to be inverses of each other, which means that, for example, these have to be the same, right? Which means that these have to be the same, and these have to be the same, and therefore those have to be the same. Yeah, so it's wrapped up in the, you know, this point of view on similarity requires that we sort of stick to that. Yeah, it's a great question. Thank you for that. Anybody else? Okay. All righty. All right, now here's a reasonable question you might ask. This point of view on diagonalizability. My punchline there was that, you know, we can think of T as being fundamentally simple, and simple in what sense? Well, simple in that we can think of it with a diagonal matrix. Reasonable follow-up question: what's so great about diagonal matrices? Why diagonal, right? Why not reduced echelon form or something, right? So what's so great about diagonal matrices? Well, diagonal matrices have some really nice features. So does reduced echelon form. Diagonal matrices, though, have certain nice features that are going to allow us to do things with this change of basis point of view that ultimately will let us solve differential equations. And the diagonal, the nice features of diagonal matrices are what's going to make that work nicely. And I have to simply punt on that and say we'll be able to talk about that in more detail when we get into Chapter 6. That said, I will go ahead and show you right now one really nice thing about diagonal matrices, which is not terribly far off from what we're ultimately going to find in Chapter 6. And that's this. Diagonal matrices have super convenient eigenvalues and super convenient eigenvectors. And roughly speaking, the standard basis vectors are the eigenvectors. The diagonal entries are the eigenvalues. And that's just really, really conveniently observable. So rather than write out a detailed proof of this, I don't think that's a good investment of time. Let me just show you, some, I think, very persuasive examples. Let's look at a diagonal matrix here. Let's say like that. And I ask what matrix or what vectors can we multiply to have the feature that we will get a scalar multiple of that exact same vector. And let me just persuade you that the standard basis vectors work. So, for example, we put in 1, 0, 0. There's our first standard basis vector, right? E1. What happens when you do that multiplication? Arithmetic. You get 6 times 1, 0, 0. There it is. Right? So the first standard basis vector is an eigenvector, and notice the eigenvalue is the first diagonal entry. Just works, right? You can see how that arithmetic is going to work. Analogously, the second standard basis vector, 0, 1, 0. Multiply that out, and you get 2 times 0, 1, 0. So second standard basis vector is an eigenvector. Second diagonal entry is the eigenvalue. We could formalize this. I think this is pretty darn believable, though. So let's just leave it at that. But it's a very nice observation to make that this does always work. Okay. Alrighty. Okay. Now, there's a little bit more language we have to talk about before we can start computing. Let's go back up to here and talk about diagonalizing. Diagonalizable. A matrix is diagonalizable if you can diagonalize it. Plausible terminology. Here's another way we say that. The process of diagonalizing a matrix is to take the matrix and to put it into diagonal form. People talk that way a lot. And let me remind you, we've talked that way ourselves in a different context. Think back to chapter 1. We talked about row reducing a matrix, right? But the other way we said it was we talked about putting a matrix into reduced row echelon form. Y'all remember that terminology, putting a matrix into reduced row echelon form? So putting a matrix into a form, very common terminology to describe, the action of doing certain things, the result of which is a certain form. Now, that language has always bugged me for the following reason. If you are doing something to put a matrix into the form, you're changing the matrix, right? The matrix that you start with, let's just talk about row reductions. If you start with a matrix A, when you do stuff to it, the resulting matrix is not A. This is a different matrix. In what sense are we putting the matrix into a form if the matrix is no longer the matrix? It's no longer it. So are we putting a matrix into a form, or are we just changing it? And how can we how can we come to grips with this terminology of putting a matrix into a form? So ultimately, it's kind of sloppy language, but this is how everybody talks, and it's fine. But I do want to give away the big point here, and what we are talking about is that something underlying the matrix, in both cases, something is being preserved. Ultimately, really, that's the thing that we should think of as putting into a form. So let me go down to my little table down here and walk us through the conversation here. So let's momentarily, don't think about this yet. Let's just think about row reductions. What were we interested back in chapter 1? Section 1.1, we were interested in solutions, null spaces, so homogeneous solutions. Remember, that's what we were ultimately interested in, right, was homogeneous solutions. That's what two matrices have in common when we say that they are equivalent. Equivalent is a useful term because it means two matrices are representing the same thing that we actually care about. Okay. So this is what's not changing in the process of a row reduction. Now, what are you allowed to do? You're allowed to fiddle with this matrix, right? Why are we allowed to change the matrix? In what ways are we allowed to change the matrix? We're allowed to do, keep in mind when you're doing a row reduction, you're allowed to do row operations. AKA, you're allowed to multiply by elementary matrices. Why are you allowed to do that? Aren't you changing the matrix? Yes, you are changing the matrix, but you're not changing the solution set. The thing we really care about, our goal to understand when we were looking at matrices in section 1.1 was to understand the solution set. The whole point to row operations is that they were reversible, aka they don't change the underlying solution set. Okay. So when we say putting a matrix into reduced row echelon form, there's our reduced row echelon form. various rules about pivots and columns and zeros and stuff. Right? Putting a matrix into a form, the matrix changes. We started with one matrix, we ended with another matrix. Yeah, it changed, but we don't care about that. We're not really ultimately interested in the matrices. What we're interested in is their shared, unchanged, preserved, homogeneous solution set, null space, whatever you want to call it. Right? So a better way, in my humble opinion, to just talk about this process of putting something into reduced echelon form is we're really putting the solution sets into reduced echelon form. We started off with a solution set that we couldn't really understand because it's in some random form. It's represented by a matrix that we don't like. We're not going to do anything to the solution set. We're just going to change the way we represent that solution set by putting the solution set, same solution set, into a different form. The solution set doesn't change. The way we represent it with a matrix does. Okay, so the reason that you're allowed to do row operations is because it preserves what we care about. Okay, everybody on board? This is just a kind of a rehash of our point of view in section 1.1. So now I want to point out that there is and I almost said similar, yikes, an analogous point of view about diagonalization. So we're going to talk about putting a matrix into diagonal form, diagonalizing a matrix. In what sense, when you change something, are you getting a new version of it if it's not it? I mean, it's changed, therefore it's not it. What do you mean you're putting it into a form? That doesn't make any sense. Well, just like with row reductions, really what we're interested in this context, we're interested in understanding linear transformations. The process of diagonalization is a statement of, I am interested in the linear transformation that a matrix represents. I want to preserve that linear transformation. I am therefore going to do things such as change of basis that don't change the underlying linear transformation. If you do a change of basis, you're not changing t, you're just changing the language that you're using to represent it. I don't want to talk in V language, I want to talk in V prime language. The linear transformation stays the same. So you're allowed to do things like change of basis. Don't forget change of basis is a conjugation that we observed recently. Right? Conjugation, same as a change of basis. The reason you're allowed to do conjugations, aka change of basis, is because it preserves what we really care about. And so this process of diagonalization, don't think of it as putting a matrix into diagonal form. The matrix changes. Right? Think of it as the underlying shared preserved thing. The linear transformation in this case. That linear transformation that was represented by one matrix, we're going to represent that linear transformation by a different matrix. It's the linear transformation, how we're representing the linear transformation, that is changing form. So we're representing the transformation. The matrix is just a tool in that representation. So anyway, there's a strong analogy here, and do keep it in mind. And again, when you hear this terminology, putting the matrix into reduced echelon form, putting the matrix into diagonal form, diagonalizing, same as putting it into diagonal form. There's a lot of subtext, there's a lot of sort of implication with that language. When you hear the word putting it into reduced row echelon form or row reducing, the subtext is that we're interested in solution sets. We're doing things that preserve solution sets, and we're trying to represent the solution sets in a way that's as convenient as possible. Likewise, when you hear the word diagonalization or putting a matrix into diagonal form, what you're supposed to infer, right? The subtext there is we are interested in a linear transformation. You're allowed to do things that don't change, that preserve that linear transformation. We want to represent it in a way that helps us understand that linear transformation as conveniently as possible. So that's all sort of hidden inside of that word diagonalizing. One last thing to keep in mind is these are separate conversations. All of this is subservient to the point of view that I'm interested in homogeneous solutions. All of this is subservient to the point that I want to understand linear transformations. You cannot mix and match, right? I see students do this all the time. Fundamentally, those students are missing a big point here. If you are trying to solve a system of equations, you cannot conjugate, right? Conjugation does not preserve solution sets. It just doesn't. It preserves linear transformations that are not what we care about when you're looking for solution sets. So don't think of this as an alternative path to get into reduced echelon form. Not at all, right? And likewise, if you are diagonalizing, you cannot do row operations. Doesn't make any sense. Row operations do not preserve underlying linear transformations. They just don't. So do keep that in mind as well. Okay, we look like we're out of time. We'll pick up here on Monday. Y'all have a good weekend. Go Duke.